In this part of the lecture series on electrostatics and Coulomb's law, I will be covering two more theory topics, that is vector form of Coulomb's law, and then I will do the superposition principle. Now what happens, as we were doing numericals, it was okay to find out force on a charge due to 2 or 3 other charges, because you can find out the mutual forces and then calculate the vector sum by using parallelogram law of vectors. But what if there are a number of charges, and what if there is a continuous distribution of charges? It would not be possible then to find out individual forces on a particular charge and then keep on calculating the effective vector sum of every pair. That will become really cumbersome. So when there are a number of charges or there is continuous distribution of charge, it is better to follow vector approach. How do we do that? First, I will see, let's say there is a charge Q1, or let's say simply Q, and there is another charge Q0. You wish to find out force on Q0 due to Q in a vector form. So obviously, let's say Q and Q0 are of same polarity. That means Q is pushing Q0 with some force, let's say F, and I call that F01. We'll be following this approach throughout in this chapter, that if I write down F12, that would imply force on Q1 due to Q2. And if I write it down as F21, by convention, what's the convention now? This F21 would represent force on Q2 due to Q1. Is that okay? So let's follow this convention, and this Q1 is exerting some force on Q0, and I have written that force as F01. Let's say the position vector of Q1, the vector representing the position of Q1 in coordinate space, is, let's say, R1, and the position vector of Q0 is, let's say, R0. Now, what would be this distance? It is easy to do that. Let's say I call this vector as R10. R10. R10 is a vector from Q1 towards Q0. If you simply apply a triangle law of vectors, what you can see, R1 plus R10 is equal to the resultant vector, which is R0. I hope it is clear. So what is R10? This is equal to R0 minus R1. What is the magnitude of this vector R10? That means what is the length or the distance between the charges Q1 and Q0? The magnitude R10 would be given as R0 minus R1. And if I ask you, what is the direction of this vector R10? The direction will be given by a unit vector R10 cap. The direction of that R10, the direction of that unit vector R10 cap can be written as the given vector divided by its magnitude. That's how you find out a unit vector. How do you find out the unit vector? You divide the given vector by its own magnitude. So what was the vector? The vector is R0 minus R1 whole divided by its magnitude, which is R0 minus R1 modulus. So once I know the direction and the distance between the charges, I am ready to apply Coulomb's law. Let's do that. The force F01 is given as 1 by 4 pi epsilon naught, the product of the charges, that is Q0, Q1, divided by square of the distance between them, that is the magnitude of this vector, which is r naught minus r1 modulus the square, and then I need to give the direction to this magnitude, direction of this force. The direction is given by r1 naught cap. You can put in the value of r1 naught over here. So what do we get? F naught 1 is equal to 1 by 4 pi epsilon naught q naught q1 divided by r naught minus r1 whole square into, I am writing down the value of r1 naught from here as r naught minus r1 whole divided by r naught minus r1 modulus. Now you have got two powers over here of this modulus and one power over here. I can write it down as f naught 1 as 1 by 4 pi epsilon naught q naught q1 divided by r naught minus r1 whole cube, the modulus whole cube, multiplied by the vector r naught minus r1. This is the expression for force which is acting on q naught due to q1 in vector form. Now, can we do the other way around? What is the force which is acting on q1 due to q naught? Now, q naught is pushing q1 in that direction. So, f1 naught would be shown less that way. What is its expression? You don't have to solve everything. What you do, you write it down as f1 naught from here. What you do? 1 by 4 pi epsilon naught q naught q1, the charges are still the same, even the length is same. Now this thing, the modulus represents the length. Whether you calculate length from q0 to q1 or the other way around, it is going to be the same. So that means basically inside the modulus, whether you write down r0 minus r1 or you write down r1 minus r0, that would be identical. So what is over here? I write down r1 minus r0 whole cube, but this is not modulus, this is a round bracket and a negative sign matters here. So what do I do? r1 minus r0. This is the expression for force on q1 due to q0. If you have noticed something, this thing remains same for both of them. That means both the charges are pushing each other with the same force. It's a mutual force. Even if one charge is bigger, the other charge is smaller, the smaller is exerting as much force on the bigger charge as the bigger is exerting on the smaller charge. But the only difference is that of direction. One is acting in this direction, the other is acting in the other direction. And that is being reflected in this bracket. I've got r0 minus r1 over here and r1 minus r0 over here. So it is very easy to say that f1 naught is nothing but negative of f0 1. In other words, you may also write it down as f1 naught plus f0 1 is a zero vector. What does it mean? First of all, you can say that Coulomb's law is compatible with Newton's third law of motion because the two are exerting equal and opposite forces on each other, which is nothing but Newton's third law of motion. And then another way of looking at it is that sum of two internal forces is zero. These are internal forces. The Q1 is exerting on Q0 and vice versa. The sum of those two internal forces is a zero vector. So this is first part of it which I wanted to solve. But one thing I must suggest you is to carefully keep this thing in mind, that while writing down the expression for a force, what we are going to do, everything else will remain same, 1 over 4 pi epsilon naught, q1, q2, whatever. But you need to write down the position vector of the charge on which you wish to calculate the force first minus the position vector of the charge due to which you are calculating the force. So if I am calculating force on Q1 due to Q2, I will write down R1 minus R2, and if I am calculating force on Q2 due to Q1, I will write down R2 minus R1. This is going to be helpful in coming questions. Just keep this thing in mind. Okay, now what if there are a number of charges? What if there are a number of charges and we wish to find out force on one charge due to all other charges? No problem. Just calculate force due to each individual charge on the given charge in this form and take a vector sum. The resultant force on a given charge is vector sum of individual forces exerted by each of the given charges. This is what we call as superposition principle. Let's see what do we do with that. Let's see. Let us assume that there is a charge Q0 with position vector R0, and there are other charges like Q1 with position vector R1. Now Q1 is exerting force on Q0 like this, and the force following the earlier convention which we developed is written as F01. Let's say here is charge Q2 and the position vector is R2, and Q2 is exerting some force on Q0 as F02. And there are other charges, let's say, so on, I've got charge Qn with position vector Rn, it will be exerting force F0n. What is the resultant force on Q0? The resultant force is force due to the first charge, force due to the second charge, plus so on up to force due to the nth charge. You may ask me, what? I'm showing the vectors always outwards. What if the charges are negative, or that means of different polarity? They might be attracting, not always repelling each other. No issue at all. While solving numericals using vector approach, if a charge is negative, you simply put negative sign with it. What will happen? Automatically the direction of force will get reversed. You don't have to worry about it. When you were solving numericals without vector approach, then you have to think of the direction. But when you are doing it with vector approach, you simply don't have to consider in which direction the force is acting, whether it's attractive or repulsive. You just keep on putting the actual signs of the charges, whichever positive or negative given. So, what would be the total force? I know 1 by 4 pi epsilon naught would be there in each of the terms, so I'm taking 1 by 4 pi epsilon naught as common. What is the first charge? Now keep that expression which we obtained earlier in your mind. It will be Q0 Q1. Since I am calculating force on Q0, I will write down the position vector of charge Q0, that is R0 first, minus the position vector of the other charge which is exerting force on Q0, that is R1, modulus whole cube, and then vector R0 minus R1 plus. Now you can try. What would you do for the second part, which is the force on Q0 due to Q2? It will be Q0 Q2 divided by magnitude of R0 minus R2 whole cube R0 minus R2 plus so on up to the last charge. The last charge was it will be Q0 Qn divided by the modulus of R0 minus Rn this time, obviously following the same approach, R0 minus Rn. This is the final expression and you can write it down in a really compact manner using the sigma sign, and you can see Q naught is also common in every term, so I am taking Q naught also common out here. Q naught over 4 pi epsilon naught, and I write down sigma, that is summation. I varies from 1 to n. What do we have? Q1, Q2, Q3, that means Qi whole divided by, what do we have? Modulus of R0 minus R1 whole cube, modulus of R0 minus R2 whole cube, and so on. That means R0 minus Ri whole cube, and the same thing in round bracket in numerator. This is the final expression for force on a given charge due to arbitrary distribution of other charges. We'll solve one numerical using this approach. Let's see how to do that. Let's say the question says that there are 4 charges, Q1, Q2, Q3 and Q4, and you have to find out force on, say Q1 due to Q2, Q3 and Q4. What we are going to do? Let's say the position vectors are given as R1 is whatever, 3i cap plus 4j cap plus 2k cap, R2 is I cap plus 3j cap plus 4k cap, R3 is I cap plus 2j cap plus k cap, and R4 is minus I cap minus 2j cap plus 3k cap. I have just written arbitrary values for these position vectors and say Q1, Q2, Q3, Q4. Q1 is 3 millicoulomb, Q4 is 4 microcoulomb, Q3 is 5 microcoulomb, and Q4 is minus 6 microcoulomb. I have intentionally given one charge as in millicoulomb and others in microcoulomb, simply because their product will make it 10 raised to the power minus 9, which will get cancelled out with the factor 9 to 10 raised to the power 9 coming from 1 by 4 pi epsilon naught. So what I can do? Let's find out the force on Q1. I know the total expression for force would be what? Total expression for force would be, I should write down 1 by 4 pi epsilon naught Q naught, and then what do I have? I've got Q1, not Q naught, I should write down Q1, then Q2 divided by R1 minus R2 whole cube, R2 minus R1 minus R2 bracket, then Q3 divided by R1 minus R3 whole cube into R1 minus R3, and then I can write down Q4 divided by R1 minus R4 whole cube, R1 minus R4. So before putting in the values, what do? I solve these modulus first of all. What is R1 minus R2? You have got R1, you have got R2. So what is R1 minus R2 vector? Simply subtract it. 3i cap minus I cap, I have got 2i cap, 4 minus 3, j cap, 1j cap, 2 minus 4, it is minus 2k cap, and the magnitude of this vector is square root of 2 square plus 1 square plus minus 2 square. So it is 4 plus 1 plus 4, which is simply equal to under root 9, that means 3. What would be R1 minus R3? R1 minus R3 vector is 3 minus 1, it is 2i cap, 4 minus 2, it is 2j cap, and 2 minus 1, it is plus k cap. So what is the magnitude of R1 minus R3? It is going to be square root of 2 square plus 2 square plus 1 square. It is 4 plus 4 plus 1. Again, it turned out to be 3. Now, let's find out what is R1 minus R4. R1 minus R4. 3 minus 1, it is 4 I cap. 4 minus 2, it is 6 j cap. And 2 minus 3, it is minus k cap. The magnitude of R1 minus R4 is going to be square of 4, square of 6 and square of 1. It is 16 plus 36 under root of 16 plus 36 plus 1. It turns out to be 36 and 46 and 52 and 53 under root 53 units, whatever. Now, in Q2, Q3 and Q4, I'll have microcoulombs. That means 10 is power minus 6 factor is present over there. That 10 is power minus 6 factor I am taking out common. 1 over 4 pi epsilon is 9 to 10 is power 9. Q1 is 3 millicoulomb. 3 into 10 is power minus 3, and that 10 is power minus 6 factor coming out of the bracket. And then Q2 is 4 divided by, the magnitude was 3. So it is 3 cube into the vector 2i cap plus j cap minus 2k cap. 2i cap plus j cap minus 2k cap. I hope I am not doing anything wrong. Plus, mathematically, okay, see, Q3, it is 5. Q3, it is 5 micro, we have already taken account of that. 5 into R1 minus R3 was this 2i cap plus 2j cap plus k cap over divided by its magnitude is also 3. So cube of 3 plus Q4. Q4 is minus 6. So I will put minus 6. That means this plus sign would become a negative sign. 6 R1 minus R4, which is 4i cap plus 6j cap minus k cap, and magnitude of that was under root 53 whole cube. This can be simply algebraically solved further. You can these 10 to minus 3, 10 to minus 6, 10 to power 9 will get cancelled out. 9 to 3 it is 27 and something in the bracket. You can take out the coefficients of I together, coefficients of j together and coefficients of k together, and this question can be solved. Now this was for 4 charge system. Even if there are 10, 20 or 100 charge systems, simple vector approach can be applicable. Obviously for solving numerical purposes there are not going to be questions more than 4 or 5 in charge systems, but still the same approach can be generalized and can be used for finding out force and individual charge due to any number of other arbitrarily distributed charges. Thank you.